Hey guys, so my name is Seturaman. I'm the co-founder of Web3Compass, and unless you have been living under some kind of digital detox rock, you've probably heard about the 30 days of Solidity challenge that we are running. It's actually our third season, and this time you won't be learning Solidity. You won't just be learning Solidity. You're also going to learn something way bigger and cooler. So yeah, let's just jump right in. All right. Now picture this. You're a developer who has been building on Ethereum. You love Solidity. You got your MetaMask set up perfectly, and Foundry and Hard Hat are basically like your best friends. But then you hit that wall. You know, the one with gas fees that makes you cry, or the slow transaction times. And you also keep hearing about all these amazing features in other ecosystems that you just can't access, like native order books or cross-chain messaging without bridges or sub-second finality. Yeah, good luck getting those while staying in your comfy Ethereum zone. Well, all of us have been there. So what if I told you that there are blockchains out there that lets you write Solidity, use all your favorite Ethereum tools, and still lets you tap into the capabilities that simply doesn't exist on traditional EVM chains. And all that without the headaches of bridges or hacks or wrap tokens or selling your kidney to pay the gas fee. Yep, I think as it's pretty clear from the title, we are basically talking about the injective protocol. And trust me, by the end of this video, you're basically going to wonder why everyone isn't building on it. Just trust me on this. All right, let's just cut through all the marketing fluff and get real for a second. You see, Injective is basically a layer 1 blockchain that has been making quite the wave in the DeFi space. But calling it just another L1 is like calling a Swiss Army knife just another knife. So here's what makes it actually super cool. First off, it's purpose built for DeFi and financial applications. Not NFTs, not gaming, not trying to be everything for everyone, just razor sharp focus on financial applications. That means every decision, every optimization, and every feature is designed with trading, lending, derivatives, and all those fancy financial terms in mind. Second, and this is where things get spicy, it runs both an EVM layer and a sophisticated Cosmos native module in perfect harmony. Typically, and you know this, like you know how most blockchains makes you choose. Either you're writing Solidity for the EVM or you're building on their native stuff, right? But with Injective, they say, why not both? And actually pulls it off. Injective is basically built on the Cosmos SDK, which means it inherits all the good stuff from the Cosmos ecosystem, like the inter-blockchain communication protocol for cross-chain communication, native staking mechanisms, the whole deal. But instead of forcing you to learn an entirely new development paradigm, they have added a fully featured EVM layer on top. So you get the best of both worlds. Write in Solidity like you're used to, but with the access to capabilities that would be typically out of scope for a regular Ethereum dev. And third, it is ridiculously fast and cheap. We are talking about a blockchain that can handle thousands of transactions per second with gas fee measured in fractions of a cent. Try doing that on Ethereum mainnet without taking a loan. Still not convinced? All right, let me actually hit you with some numbers then. I know, typical salesman pitch, but here's the thing. Injective offers native interoperability with over 120 blockchain networks through the IBC and cross-chain bridges. It actually has an MVV resistant order book that protects you from front running. Yeah, for real. And earlier this year, they introduced multi-VM token standard that makes tokens work seamlessly across both Cosmos and EVM environments. And to top it all off, they offer transaction finality in under 1 second. Not theoretically, not eventually, but actually. But here's the thing that really matters. Injective didn't just bolt an EVM onto the blockchain and called it a day. They actually built something fundamentally different, a true hybrid environment where both EVM and Cosmos are like first class citizens. And one of the secret sources that makes all these come together is what we call precompiles, and we'll talk about them next. All right. Now, before we dive into Injective's precompiles, let's just get our precompile basics right. You see, on most blockchains, Smart contracts are just programs that run on top of the blockchain's virtual machine. Of course, you already know that. Take Ethereum, for example. When you deploy a smart contract, it gets, I mean, a Solidity smart contracts on Ethereum, it gets compiled into EVM bytecode, and the Ethereum virtual machine executes it line by line, opcode by opcode, and it works. But the thing is, it's slow and expensive because the EVM has to interpret every instruction at runtime, validate it, and track the gas cost for each tiny steps. Now, enter precompiles. Now, these are in your usual smart contract. You see, instead of being deployed bytecodes that are interpreted by the EVM or other virtual machines, precompiles are basically native codes that are baked directly into the blockchain. Think of them as shortcuts or cheat codes that skips the VM entirely and run super fast optimized functions. On Injective, these precompiles are written in Go, the same language the blockchain itself is built with, and they are placed at specific predefined addresses in the virtual machine. You see, and when your Solidity contract calls one of these addresses, the EVM doesn't just run bytecode step by step. It just executes the native Go functions directly. And the result is that you get operations that are orders of magnitude faster and cheaper and more powerful than anything you could implement in pure Solidity. So, blockchains usually provide precompiles mainly for the performance. I mean, some operations are just too heavy to run in interpreted bytecode. Ethereum, for example, has precompiles for things like recovering addresses from signature, hashing functions, etc. And these precompiles, they live at very specific addresses, and calling them runs the native code through the EVM. And this is precisely where Injective gets clever. You see, most blockchains use precompiles just for low level crypto functions, but Injective, well, they take it a step further. They use precompiles as basic bridges between the EVM and the native Cosmos SDK modules. That's the magic right there. You see, the precompile makes the whole dual environment system actually work, letting you write Solidity while seamlessly tapping into the Cosmos native features at the same time. Now, I know all this can sound a bit confusing, but let's just explore this whole thing a bit further. All right, explanation time. Remember when I said Injective runs both an EVM layer and native Cosmos modules, and precompiles are basically like hot sauces or something? Well, here's how all that actually works in practice. You see, when you look at Injective, at the bottom layer, you have the Cosmos SDK modules written in Go. Now, these modules handle the core blockchain functionality. For example, you have the bank module, which manages native token balances and transfers. You have the staking module, which handles validator staking and delegations. You have the governance modules, which manages on-chain proposals and voting. So different modules handle different stuff, right? Now, these modules are fast and efficient and battle tested. I mean, they are the same proven infrastructure that powers dozens of successful Cosmos blockchains. And at the top layer, you have the EVM. This is where your Solidity contracts live, where MetaMask connects, where all the Ethereum tooling works. It's a complete, fully functional EVM implementation that behaves just like Ethereum. Now, the problem is these two layers, they speak completely different languages. The EVM knows about Solidity contracts, gas, ERC20 tokens, etc. And the Cosmos modules know about the native denomination, staking validators, and IBC packets, etc. So the question is, how do they communicate? Well, that's right, precompiles. Now, these precompiles, they in Injective, they basically act like these fancy translators. You see, when your Solidity contract calls one of these precompile functions, here's what happens. So your contract makes a normal function call to a precompile address. The EVM basically recognizes this as a precompile address and hands off the execution to the precompile Go code. And the Go function basically executes against the native Cosmos module state, and the result is returned back to your Solidity contract, and execution continues in the EVM as if nothing happened. And I don't know if you have noticed this, but the absolute beauty of all this is that both these environments are reading and writing the same underlying state. There is no EVM version or native version of your token or data. There is just one set of data in the native module with both the EVM precompile and the native Cosmos transaction reading from and writing to the exact same data. Still a bit abstract? Let me give you another analogy that will make it all click. Imagine you are in a building with two floors, right? The top floor is the EVM world. Everyone speaks Solidity, uses MetaMask, lives their best Ethereum life. And the bottom floor is basically Cosmos native module world. Handling staking, governance, token management, and all that beautiful on chain order books and everything. In most blockchain architectures, these flows they don't talk to each other. But if you want to make them talk, you would need to build complicated elevators that we call bridges, have people carry messages back and forth, reliers basically, and deal with maybe two separate versions of everything, wrapped tokens. And so if you want to move assets between the floors, lock them up on one floor, mint a representation on the other, pray that nothing breaks, and pay fee for every round trip. Now, precompiles are basically like having a magic intercom system in that whole building. You just pick up the phone on the EVM floor, dial a very specific number, which is basically the precompile address, and suddenly you're talking directly to the person on the native module floor. No elevator ride, no message passing, no wrapped anything, just instant direct communication. And even better, when something happens on the native floor, say someone transfers token using a Cosmos wallet, it's instantly visible on the EVM floor. No waiting, no syncing, no hoping, no reliers, no anything, because there aren't two separate token balances or data. There is just one data or one balance stored in the native module, and that both floors have direct access to. So when someone on the EVM floor sends token, the native balance updates. Someone on the native floor sends token, the EVM balance updates. It's not synchronization, it's the same data access through different interfaces. Now tell me this doesn't sound cool. All right, let me get a bit real here, or maybe even a bit passionate, because you see, I've been building on blockchains for years now. And honestly, the isolation between ecosystems has always been the most frustrating part. I mean, you've got these incredible capabilities scattered across different chains, like, on chain order books, or faster finalities, or advanced governance modules. But as an EVM developer, you're usually stuck on the outside looking in. You want to use a native order book? Well, buckle up. You're learning a whole new language, new SDK, new everything. You want to integrate staking in your dApp? Too bad. The EVM doesn't support it natively. You will end up writing your own version, hoping that it doesn't get hacked. You want subsequent finality? That means migrating to another chain and leaving all your users behind. Meanwhile, the EVM ecosystems with millions of devs, tools, and DeFi protocols is basically locked in its own bubble. So the reality is you get what your chains offer. And if it doesn't have something, well, tough luck. And that's the wall that Injective basically breaks down. You see, Injectives precompiles don't just patch the gap, they basically bridge it very cleanly. Like, you keep writing Solidity, you use the same tools you love, but now your contracts can directly access or call all the native functionalities. No wrappers, no workabouts, no workarounds, just one function call that gives you access to the full power of the chain. And suddenly your Solidity code can place, real limit orders, take tokens, vote in governance, or manage assets all natively. Things that would normally take custom contracts or off-chain infrastructure are now basically a call away. And because of these precompiles, or because precompiles run as native Go code instead of slow EVM bytecode, everything feels fast. Cryptographic operations, transfers, trades, they all execute blazingly fast at a fraction of the gas cost. You also skip the entire bridge mess. No wrap tokens, no split liquidity, no scary bridge exploits. Both the EVM and the Cosmos side simply interact with the same token and the same state one asset, one balance, two ways to access it. So from a developer's perspective, it kind of feels unfair. I mean, you're still using Solidity, Foundry, Hardhat, all your familiar tools, but now you can tap into the features that most EVM chains can't even dream of. No need to learn Rust or Go, no IBC packets or protobuf decoding nightmares, just clean, simple function calls that handles everything behind the scenes. And the best part, it's all composable. Other contracts can call those same precompiles too. You can have DAOs trading on native order books, yield protocols taking ideal assets, or aggregators combining strategies across modules, all talking to each other seamlessly. And Injective didn't just make Solidity work on Cosmos, it basically superpowered Solidity. And precompiles, well, like I said, they're basically like the secret sauce behind all this. All right, I'll admit, I might have gotten a bit too carried away in the last part. So let me just take a breather, cool down for a second, and actually talk about what this video is supposed to be about: the bank precompile. Now, this one's special. I mean, it's the precompile you'll be probably using the most. And honestly, it's where Injective really flexes what it can do. So, what exactly is the bank precompile? Think of it as your all access pass to the Injective's native token management system, the engine that basically handles everything from sending and receiving tokens to keeping track of balances. Basically all the essential stuff that keeps your dApps economy running smoothly. But here's where it gets really interesting. I mean, in the traditional blockchain world, if you launch an ERC20 token on Ethereum and wants to use it elsewhere, you've got a whole ritual waiting for you. I mean, lock your tokens in a bridge contract, mint wrapped versions on the other chain, hope the bridge doesn't get hacked, juggle two token addresses, pay annoying fees, wait for confirmation, and lose a tiny bit of your soul every time something breaks. But Injective just says we are not doing that. You see, when you create an ERC20 token using the bank precompile, your token doesn't live in some isolated contract. It lives directly in Injective's native bank module, the single source of truth. The EVM simply gives you a familiar ERC20 interface for it, while the Cosmos side recognizes it using its own unique denomination. And here's the cool part: it's not two tokens pretending to be one, it's one token with two interfaces. Sending it using the ERC20 transfer function in MetaMask, the native balance updates instantly. Sending it using a Cosmos wallet like Kepler, the ERC20 balance of function reflects it right away. No bridges, no wrapped assets, no reliers, no waiting, just one token perfectly in sync between two worlds, EVM and Cosmos, like they were always meant to be connected. Yes, I know. I've been yapping a lot about injective precompiles and the bank precompile. And you guys are basically itching for that sweet, sweet code. But before we actually play around with the bank precompile, we have to ask a very practical question. How do you call these things from our Solidity code? Well, that's where interfaces comes in. So, what exactly is an interface? So, for all the beginners out there, think of interfaces as these maps that tells your Solidity code how to talk to an other contract. Right? It defines the functions, the parameters, and the return types just like any other contract, but it doesn't contain any actual logic or state. It's basically like a roadmap and not the car itself. And honestly, if you have ever worked with interfaces in Solidity before, this is going to feel very familiar. Okay, so in Injective, the bank precompile is sitting at address 0x64, quietly doing all its native module magic in Go code compiled directly into the blockchain. But your Solidity contract can't just randomly call functions on an address and hope they work. You need a way to tell your contract that at this address there is something that understands these specific function calls, that takes these parameters and that returns these values. This is exactly what an interface does. It doesn't have an implementation code, no state, no logic of its own. It basically tells your Solidity compiler that when I call this function, format the call data like this, send it to this particular address, and expect this return type back. Now, here's a look at what's available through the bank precompile interface. If you have worked with ERC20 tokens, a lot of this will look familiar. Now, Injective doesn't just leave you with the interface and say good luck. They also provide ready-made contracts like the bank ERC20.sol, which is an abstract base contract implementing ERC20 backed by the bank precompile. You can extend it for your own tokens. And all of these pre-built contracts uses OpenZeppelin's battle-tested contracts. So you're not starting from scratch, you're actually starting from a solid audited foundation. You don't have to reinvent the wheel every time. And that's it officially. Like, all the yapping is done. Now we are going to code. All right, now that we are all ready to get started with the coding, I guess it's time we look at all the tools that we are going to use to create our bank precompile smart contract, or smart contract that uses the bank precompile. So the thing is, if you have tried Solidity before, or if you have researched a bit about Solidity, I'm pretty sure you might have come across these terms like remix and hard hat. Now, remix is what you call a browser based Solidity IDE, meaning it's sort of like your VS code and stuff, but it works entirely on your browser and it helps you write Solidity smart contracts, right? Like, you don't have to install anything, you don't have to do any kind of setup. Just go to Google and just type in a Remix IDE, and it will take you to the sleek editor, right? You can quickly get started with writing your Solidity smart contracts. Like, it's super easy, and it's the best way to get started with Solidity, especially for somebody who is new. And like, it comes with a lot of uh, tools, like easy to use tools where you can compile, where you can deploy and test your code. So yeah, I mean, really great tool. But like, now when you go to something like hard hat, now this is a bit more advanced stuff. Like, this is a complete Ethereum development environment, and what it does is, it's way more powerful, in a sense that it actually lets you run local blockchains, write automated tests, write scripts for deploying contracts and stuff. Like, the whole idea is, it helps you manage a Solidity project in your system, right? And you can manage that project in a very professional manner. Like, it has all that folder structure and everything handled. So it's a really powerful framework for writing, testing, and deploying your contracts. And it's pretty much, like, it's very widely used in the Ethereum ecosystem. So if you are familiar with any of these, good for you. Like, all, like, whatever we are going to build, it will sound super simple for you guys. Now, the thing is, there is yet another framework. I think we'll be using that in our current tutorial, and that is called Foundry. Now, the thing about Foundry is that Foundry is basically built for speed. I mean, like, if you really want to test out things faster, and if you want a much more lighter framework, and something that has like, that is quite easy to handle, like, let's say, like, you just, all you have to do is type in a couple of terminal commands, you use Foundry, right? So Foundry is actually written using Rust, but all the scripting and everything is done using Solidity itself. So if you are new to Solidity and stuff, I think Foundry would be the next best framework to pick up, because everything is still in Solidity. You don't have to learn any other language. Like, you can start with Foundry because you already know Solidity. So we'll be using Foundry for this. And like I said, Foundry is basically designed for speed and efficiency, right? It helps you compile, test, deploy contracts, everything, with super fast scripts and commands and everything. And it also comes with a lot of really, really cool tools, which we'll see. So it's pretty easy to install Foundry. Like, all you have to do is, you have the commands right here. You just have to open up a terminal. Oh, wait, just clear this. You just have to open up a terminal, copy this, paste it. I mean, I've already installed Foundry, so it's, yeah. And then you have to give the Foundry up command. So yeah, the Foundry app basically helps you install all the tools that I talked about, right? So like at this point, I think it's worth mentioning all the tools that Foundry, installs. Like the first one is Forge, which is basically your main workhorse. Like it helps you compile contracts, create projects, run tests, and everything. Then there is Anvil, which basically helps you spin up a local Ethereum compatible blockchain so you can test your contract safely and quickly. And finally, we have something called Cast. Now, this one lets you interact with contracts and nodes directly from your terminal, whether it's sending transactions, calling functions, or querying data. Cast you can use cast commands to actually interact with the chain. So together, these tools make working with Solidity much more faster, simpler, and way more fun. So once you have installed all this, to check if Foundry is properly set up in your system, all you have to do is just type in the command forge version. And if you get the proper version, that means Foundry is good to go. All right. Now that we have Foundry installed in our system, the next step is to actually configure all the things that are required to interact with the Injective testnet. Now, those who are already familiar with the blockchain development lore, you guys know what a testnet is. So for those who are new, you see, when you develop a new contract, you don't directly put it onto a main network like the Ethereum mainnet or the Injective mainnet. The reason being, one, these mainnets are expensive, like relatively expensive. So, in case your contract has some bugs or issues or errors and stuff, and you put it directly to the mainnet and people start interacting with it, they are going to lose real money, and you are also going to lose real money trying to test it or trying to upgrade it or trying to change the code and stuff, right? So what you do is, like, most of these networks, they provide a test network or a test environment where you can deploy the contract and test it out before actually pushing it to the mainnet. Now, the test network actually works very pretty much similar to how a mainnet works. The only difference being, there is no cost for deploying stuff or doing stuff in the testnet, because you know you deal with test environments and you deal with test tokens, which basically cost nothing. So when you're developing a contract, the first place that you actually test out the whole thing is the test network, and every ecosystem or every chain actually has a test network, and Injective is no different. So to actually interact with the Injective testnet, what you have to do is, you need a wallet service, like you can install MetaMask. And once you have MetaMask installed, just go to the Injective docs, just go to the Injective docs, and yeah, one second. Right, go to the EVM developer section, go to the EVM network information, and there you will see the information regarding the Injective EVM testnet. Right? You have the chain ID, the RPC endpoint, all those kind of things. So what you have to do is go to MetaMask, click on this, menu icon, go to networks, click on add a custom network, and here you just have to add all these testnet details. Like, you can give the name as Injective testnet, you can add the JSON RPC endpoint here, the chain ID, like 1439 here, the currency symbol, which is INJ, I believe, and the block explorer URL if you want, right? And once you add all those details, and just then you just have to save it, and you will be able to interact with the Injective testnet. Now you can see, like, I didn't do all that because I've already done it. Like, you can see a couple of Injective testnet tokens here. You can see that I've already added all those details, and I can interact with the Injective testnet. So okay, once you have all the details added to the wallet, the next thing that you need is the Injective testnet tokens, and the place where you get these testnet tokens is what we call a faucet. Like, you have the link right here, so just click here and it will take you to this page. Now here, what you have to do is just copy this address, which is your account address, paste it here. Yeah, and request tokens. Like, I have already requested tokens before, so I might not get it, but yeah, if you're new, like, you will get those tokens. I think this faucet gives you one token, but I actually suggest, like, just copy this address, like the injective address, go to the Google faucet, which is much more generous. So you can just go to the Google faucet and paste your address there, and just click on receive 10 testnet tokens. So yeah, the Google faucet is much more generous, so you can use this one too. So once you get the tokens, you are all set. Like, you have access to the network via your wallet, and also you have some test tokens that you can use to test out your contract. Now, don't be fooled with the amount that is shown. Like, it doesn't, like, it doesn't cost that much. Okay, like, it's absolutely free. Like, there is no cost attached. So get your like, add all the details to your wallet and get yourself some test tokens, because once we have all that, we are going to set up our project and deploy our contract onto the Injective testnet. So let's go. All right. So before we actually get started with our token contract, I think it's best if we take a step back and really understand what this whole ERC20 thing is all about, right? I mean, because if you're new to Solidity, I'm pretty sure you guys have heard of this term, like ERC20. I think I've mentioned it a couple of times in our video too. And like, it's one of those terms that keeps popping up everywhere. Like, it's used everywhere. But the thing is, it's rarely properly explained, right? But if you have been paying attention, you might have figured out that ERC20 has something to do with tokens, right? It has something to do with tokens. So the one thing that you have to understand about this token business is that, it can be any kind of token, but the underlying fact is that all of it is just smart contracts. Like, underneath every token that you have seen or heard or have tweeted about, it's just smart contracts, right? So, like, it's basically a piece of code that is deployed on the blockchain, and that code basically keep track of the balances. It defines how the token transfers work, and even decides what rules govern the token's behavior. So it's all just code, it's all just smart contracts. So when you send a token, you're not actually moving coins around like in a game inventory. Okay, what's really happening is that the contract, like the smart contract that defines these tokens, it updates a number in its internal storage. Like, it subtracts some amount of token from one address, or some amount from one address, and just adds it to the another, like adds it to the other address that where you are sending the token to. So it's all logic, right? There is no actual movement of tokens. So the thing is, in the earlier days of Ethereum, like, I'm talking about 2015, 2016, when Ethereum was very, very new. So everybody was excited with the whole concept of programmable money, right? Every developer wanted to try this out or test it out. So what ended up happening was that everybody was building their own versions of these token contracts, right? Like, everybody wanted to create a token in their own name, or maybe in their pet's name, their business, for utility, whatever. So everybody started creating contracts that handle tokens, right? Now the problem here was that there was no single standard, right? Every developer wrote their token in their own way or in different ways. So for example, one contract might call its transfer function send, another might call it move tokens, and someone else might store balance under a different variable name. So it was basically a lot of chaos, because everybody was writing these token contracts in their own way. Now the real problem started when platforms or exchanges or wallets or dApps tried to interact with these tokens, because they couldn't interact reliably with these tokens because there wasn't a shared standard between them. So if they have to interact with a new token, they might have to integrate new piece of code, because the token might be using different names for its different functionalities, because everybody was writing their own versions of the token contract, right? So it was generally chaos, like when it comes to the whole token scene. So that's when the Ethereum community came together and said, all right, let's just fix this mess, right? And what these guys did is they proposed a set of common rules or standards that every token contract should follow. So if you're writing a token contract, these guys proposed a standard saying that, okay, if you're writing a token contract, follow these standards, right? And that proposal for standard became ERC20, right? So, I mean, ERC stands for Ethereum Request for Comments, and 20 is basically the proposal number. So, what it did is it basically said that if you're creating a token, just follow the rules that is given in the standard. Now, it's not like complex rules. Okay, what ERC20 did is that it defined a simple but powerful interface. It basically said that if you are creating a token, make sure that your contract includes all these functions, right? Like you can see it, like you can go to the official Ethereum page about ERC20, and it will show you all the methods and stuff. Like, you have name, symbol, total supply, balance of transfer, like you have a couple of events and everything. So ERC20 standard basically said that if anybody is creating tokens, make sure that you include all these methods, right? So the advantage here is that this brought in a standard. So if somebody says that they are creating an ERC20 token, you know the function that you can call to transfer a token, or the function that you can call to get the balance or the total supply, right? So this created a standard for defining tokens or creating token contracts, right? And if your token followed these rules, it could instantly work with any wallet, any exchange, or any dApp that basically supported ERC20. So they don't need to add any custom codes or any kind of special integration. So that is why ERC20 completely changed the game. Before ERC20, every token contract was basically different because everybody was writing it in their own way. With ERC20 standard, it turned the whole token contracts from isolated little programs into interoperable assets that could move freely across the entire Ethereum ecosystem. Now the thing is, if you know Solidity, you can basically write your own ERC20 token contract from scratch, right? All you have to do is include all these functions, right? So you can directly do it. But the thing is, writing an ERC20 token from scratch is kind of like trying to build a car, on your own, because it takes a lot of work, and it's risky, and it's time consuming, and you can easily mess it up. Like, a lot of things can go wrong. So that is where libraries like Open Zeppelin comes in. Okay, so Open Zeppelin is basically an open source library that contains a lot of battle tested smart contracts. Okay, and these contracts are audited, they are reviewed and used by thousands of projects across Web3, right? So what they do is it contains secure implementations of standards like ERC20. Like, you can just go to their documentation and you can see, like, under tokens, you can see, like, these are different token standards, and you can go to ERC20. And the thing is, they have contracts that has already defined everything. So what you can do is, when you are writing an ERC20 token contract, you don't have to write the entire function. All you have to do is you just have to import the Open Zeppelin ERC20 contract, and you can inherit it in your contract. And all you have to do is just provide all these things like the token name and symbol and initial supply and stuff, and all the other code, all the other functions and everything will basically be taken care of by the tried and tested Open Zeppelin library. So it's a very convenient way, meaning instead of writing 50 line of code for an ERC20 token, you can do it in 5, right? And like I already mentioned, like, these are like tested contracts, so you don't have to worry about security, you don't have to worry about the code optimization or anything, right? These are like proper tested contracts that you can import onto your own uh, you know a contract and create an ERC20 token with, right? So before we dive into the code, what you have to understand is that tokens are just contracts, and ERC20 is basically a standard or a shared language that makes the contracts universal. Like it is basically a set of rules that we have to follow while writing a contract that handles a token, right? And Open Zeppelin is a toolkit that makes building these tokens super simple and super safe. All right. Okay. So I guess that's the crash course. Now let's just go ahead and build our token contract. I mean, yeah, ERC20 token contract. All right. So now that we have installed Foundry and now that we have set up all the details for accessing the testnet and we got ourselves some testnet tokens, we are ready to get started with the project. So let's just go ahead and initialize a Foundry project. It's pretty straightforward. So let's just open a terminal, type in Forge in it. So since we are going to use the bank precompile, I think it like we can just go ahead and create a token. So I'll just call it dev token, like that's the name of the project. So you can just click on it and you can see a folder popping up. Now you can open the folder using a code editor. I'll use Visual Studio Code, and yeah, you can see that Foundry has already set up all the different all the different directories and files and everything. So you just need to go ahead and create a Solidity contract and deploy it, right? But we have to make a few changes here and there, like I'll show you. But first, let's just go through the directories. Like you have the lib directory, which contains all the libraries that you're going to use for your contract. Now we will be installing an additional library, like this is the Forge standard library. We'll be installing something else, which is basically the Open Zeppelin library that we are going to use for our token contract. Now you have the script folder, which contains the scripts that you use to deploy the contracts. You can see that it is written using Solidity. But the thing is, we won't be needing the script directory for this one, so you can just go ahead and delete it. Now you have the source directory, which actually contains the contract. Now like Foundry, like when you set up a project, it actually gives you a very basic contract as a reference, like as a template. You can delete it, you can rename it, you can do whatever you want with it. So like the source actually has a simple counter contract, right? And next you have the test folder, which again, as the name sounds, where you can write all the tests for your contract. Again, we won't be needing this in today's example, so let me just delete it. And then the major one is the foundry.toml file. Now this is sort of like the control center, like everything attached, every detail regarding every configuration detail regarding the project, it goes right here, right? So if you want to specify the Solidity version, or if you want to add RPC URLs or whatever configurations that you want, you do it right here, right? So I guess to start with, I will just show you guys how to install a new library in this project. Like we have a project, so we'll just go ahead and install the Open Zeppelin library so that we can use the Open Zeppelin contracts. I mean, it's pretty straightforward. Like all you have to do is just give a command. So let me just open a terminal here. Where Yeah, I'll just open a terminal here, and you just have to give the command Forge. Like I told you, Forge helps you manage the project. So Forge install, and you just have to give this. Wait, let me just copy so that it just doesn't take much time. Okay. Yeah. So this is the Open Zeppelin. So this basically maps to the GitHub repository. Like Open Zeppelin is the name of the repository, and this is the thing that we are trying to install. So yeah, once you give Forge install Open Zeppelin hyphen contracts, and press install, it will install the library. Okay, it will install all the contracts and everything. Like I don't know. Yeah, there you go. You can see that the library, like the Open Zeppelin contracts, just appeared in the library directory. Now within the foundry.toml, what we can do is we can actually add something called as a remapping, because the thing is, every time we are trying to use the Open Zeppelin library, you have to specify the location. So every time typing this whole thing is a bit too much. So what you have to do is you can just provide a shortcut like this. Oh wait, okay, a shortcut like this, which basically means that every time they see this at the rate symbol and open Zeppelin, just replace that with the actual path. So we don't have to do a lot of typing. It helps you map your key with this value. Pretty neat stuff. So yeah. So we have installed Open Zeppelin and we have created a remapping that helps us easily type out the whole path for the contracts, right? So yeah, let's get started with the contract. All right. So now that we have added all the configurations to the foundry.toml, I guess we can start with our contracts. Now there are two ways of doing this. Like there is the easy way where we write one big contract that has all our interfaces and our token contract and everything. But that's not how we do things here. So here what we are going to do is we are going to create two files, and in one file we'll have all the code for our interface, and in the second file we will have all the code for our contract. Right now the interface, as we already know, it basically defines or declares all the functions that we need to actually talk to the bank precompile, and in the token contract we will actually use that interface to interact with the precompile and add all our token functionalities. So let's just go ahead and see how we can do this. So like as you know, we are going to set our contracts in the source folder. So let me just remove this one. You can edit it if you want, but yeah, I mean, I'll just remove it. And I'll just create a new file called ibankmodule.sol. So again, this is a coding practice where if you are writing a Solidity file that contains an interface, you just put an I as the preface, oh sorry, prefix for the file name, right? Like in the file name, you just put an I as a prefix. So yeah, ibank module, it's going to contain an interface. Now there is a very easy way to get the interface. Like if you go to the uh, you know injective documentation and you go to bank precompile, you can see that it provides the interface right here. You can copy it and use it, but you might have to add a couple of Solidity stuff like the pragma and everything. So I have all that already prepared, so I'll just paste it here. So yeah, there you go. So this is what our interface looks like. It has everything like pragma, license identifier, the interface, everything. And as you can see, like there are functions, function declaration along with all the parameters and all the return functions, return data and everything. So this sort of acts like a roadmap that tells our token contract that, hey, these are the functions that you can interact with in the bank precompile. These are the data that this function takes, and this is what it returns. So act accordingly, right? So yeah, you can see like those who have already worked with YASI 20 tokens, a lot of these functions will be very familiar. Like you have mint, which basically mints or creates new token to an account. You have balance of, which gets the balance of an account of a specific token. You have burn, which basically removes or deletes token from an account. Transfer, which does exactly what the name sounds. It transfers token from the from address to the to address and get the total supply of the tokens. You have the token metadata, which gives you the name, the symbol, and the decimals of the token. And of course, set the token metadata, which helps you set the name, the symbol, and the decimals. So yeah, so this is the whole idea of our interface. Now we are going to use that in our token contract, which we will be creating now. So yeah, let's create our token contract. All right. So now that we have created our interface, let's just go ahead and get started with our token contract. So for that, I'll create a new file, devtoken.sol, and add all the usuals, spdx and pragma. I'll just put the version as 0.8.20. Pretty standard stuff. Okay. So yeah, and I'll do a bit of importing. So I'll just copy all the imports that I need. So pretty standard, like you have the Open Zeppelin ERC20 token contract. You also have the ownable token. So ERC20 gives you the framework for creating the tokens. Ownable helps you control the access, like you can set the owner for the contract, and using that you can control the access to functions and stuff. And of course we will also be inheriting, oh sorry, we will also be importing our interface. Now you know that like we are creating the token contract in the same folder as that of our interface. So that means, to in order to import it, you just have to give the dot and slash. That means this file is in the same folder as our token contract, right? Pretty standard stuff. So yeah, now to get started with the contract, right, like so you can use the interface directly. Like since we have imported it, you can use the contract, like the interface directly in our contract, and access all the precompile functions. So yeah, now let's just start with the contract. So contract dev token, and we are going to inherit the ERC20 and the ownable. And yeah, so this is the basic declaration of our contract. Pretty standard, pretty simple. Dev token is the name. We are inheriting both the ERC20 and the ownable contracts, right? So the first thing that we have to do is that we have to create the representation for our precompile. Like we have to set the address for the precompile, so that we can use it with our interface and access all the functions. So the general idea here is that, yeah, so like we basically create a constant reference to the bank precompile. And as you know, the precompile is basically at a fixed address, like the 0x64. So this address is hard coded into the injective blockchain, and it's basically acts as a special contract that bridges to the native functionalities. So let's just create a constant reference to it, so that we can use it in our code, right? So yeah, let me just do that. So for that, I'll just go I bank module private. I'll call it constant. Okay. And bank, again, this is a coding style where if it is you know constant, you just use all caps, like you know all caps for mentioning the variable, so that it's a constant. So and this is the address. So there you go. So we have created a reference. Now we are basically saying that there will be these set of functions that is given in the interface within this address. So using this bank, you can basically talk to that uh, address, like all the functions, or interact with all the functions in that address, and the whole map to that functions, like all the functions in that address is basically given as our interface. So using this, we will be interacting with the functions that is there in this address, right? That is there in the precompile, that is stored in this permanent address. So yeah, so that's how it works. All right. So moving on. Now that we have the precompile reference set, let's just add a couple of more constants and variables. The first one will be an address. It is going to be private and immutable, and this is going to be the token address. So this address, yeah, so this variable, it's an immutable variable, meaning you can initialize it once. We'll do it inside our constructor. So and we will store the token address, which will basically be the address of this contract. Like I'll show you how it is done. But since it's an immutable, it means that this variable can only be initialized once, right? You don't have to initialize it directly like we do with constants. You can initialize it anywhere else in the contract, usually in the constructor, but you can only do it once. Like you do it within the constructor, and you can only do it once. So yeah, once the value is set in the constructor, you cannot change it anywhere else in the contract. So that's the whole idea of an immutable variable. Now let's just set another constant, u into 56. It is also going to be a private constant, and this is basically our initial supply, right? So yeah, and we are going to set our initial supply as 123 into, let's just, let's just put 10 raised to 18. Yeah, again, standard stuff, right? So we have the constant. Now we will have another stuff in our contract, which is the event. So we are going to create a very basic event called bank operation executed. Okay, so the idea of this event is whenever we call one of the functionalities from the precompile, like the bank precompile, we'll just emit this event so that we get an idea of what operations that we are performing and whether the operation was successful or not, right? Like when you look at the interfaces, you can see that many of these operations return a boolean, meaning it gives you a status of whether the operation was successful or not. And there are also other ways to figure it out, like with the return types and stuff. So we will basically, this event will tell you which operation that we are doing, so operation, and also whether the operation was successful or not. Okay, so yeah, so this will give us a pretty good idea of how we are interacting with the precompile. So once that is also out of the way, let's just get started with our constructor. So with the constructor, the thing is we have to make it payable, because in order to avoid any kind of spam, like we need like when we are interacting with the bank precompile, we need to send one injective token. So even from our constructor, we will be interacting with our the precompile contract to set metadata and stuff. So we might need to pay a certain amount, like one injective token, to basically do that interaction. So we will be sending some value while we are deploying the contract, which the constructor will use and then interact with the you know a bank precompile. So that's why we are making the constructor payable. That means it will accept value, I mean, like amount that you will send during deployment, so that it can use it for interaction with the bank precompile. Like I'll show you this whole process during the deployment, but right now we'll just give the payable keyword here so that our constructor can accept payments, right, value. And we'll just give ERC20 here, and we'll just give dev token as the name, dev as, oh, okay, just put it, dev as the symbol, and ownable, and there we will just put ourselves or the person who deploys this contract as the owner. And within the constructor, the first thing that we are going to do is we are going to set the token address, and this token address is going to be the same address as that of this contract, right? Okay, next, what we are going to do is we are going to set the metadata for our token, and we are going to set it in the bank precompile, right? Now, again, this is a really really important step that you have to understand, right? Like traditionally, when you are writing a contract, like an ERC20 contract and Solidity, you store all these stuff like the metadata, like the name, the decimals, the symbol, everything. Also, you also have these mappings that keep track of all the balances, and you do all that within the contract storage itself, right? Right, like you actually use the contract storage itself to actually store all these things. But here there is a fundamental difference. The thing is, the Solidity contract that we are writing doesn't actually store or manage any of the token data. Okay, like like I said, this contract, or our, like the contract that we are writing, it is essentially a it acts like a proxy or a translator, right? It speaks ERC20 on one side so that MetaMask and other EVM tools can understand it, and it speaks to the bank precompile on the other side via our interface, right? Think of it like a bilingual interpreter, right? It doesn't make any decision, it doesn't store anything, it just helps with the a communication between the two parties. And the source of truth or the data will actually be stored in the native bank module, living deep in the blockchain's core, right? So that is where the data will reside. We will actually access it through our a bank precompile. So what you have to understand is, unlike our traditional ERC20 contracts, we won't be storing any data within this contract. Everything will be stored and accessed via the bank precompile, right? So the native bank module will basically act as the single source of truth. Now, the biggest advantage of this is that the contract, like the EVM contract as well as the Cosmos contract that you write, both of them can access that same token. I think I've already mentioned this earlier, that there won't be two instances of the token. There will be one token, a single token, and you can have different interfaces to actually access the token data, right? So your EVM contract as well as your Cosmos contract will be accessing the same token data that is stored in, or that is handled by the native bank module, right? So that is how it works. We won't be storing anything in the constructor or the contract or anywhere. We will actually be using the bank precompile to store the data, meaning it will be handled by the native bank module, right? So let's see how all this actually takes place. So we have the token address, and next we are going to set the metadata. So instead of having variables to store the names and stuff, what we are going to do is we are going to create a bool, because you can see that like there is a metadata function, like set metadata function in the interface, meaning we there is such a function in the bank precompile, and it actually returns a boolean, right? So we'll just say bool metadata set. So this gives, if the operation is successful, it will be true, else it will be false, right? And we will call bank dot set metadata, right? So we are calling this function via our interface. So this will basically pass on all this information to the bank precompile, and we will give all the information of our token, like the name, dev token, dev, which is like the symbol, and of course the decimal, which is 18, right? So yeah, we have given the data to the or we are passing the data via our interface to the bank precompile. Now we can emit the event, like we can say bank operations executed. The operation, we'll just put it as set metadata data, and of course we'll just put the success thing as, sorry, metadata set. Okay, pretty simple stuff. We call the function in the bank precompile via our interface reference, and like the reference that we have created, and based on the data we just emit an event that tells us about the operation and whether it's successful or not, right? So that is one part done. So the next thing is that once all the metadata is set, we have to mint the tokens, and we will be minting the tokens to the owner's address. So again, we'll just create, you can see that there is a mint function here which also returns bool. So we'll just go bool mint success equals bank dot mint, and the account will basically be message dot sender, and the amount will be the initial supply. Yeah, there you go. So we'll be minting all this amount and sending it directly to the message.sender. Now here we can actually use the transfer event that is part of the ERC20 contract from OpenZeppelin. So event transfer, and we will say address 0, which is like our address. So what we are saying is, from our address, which is the token address, we will be sending a certain amount or the initial supply of tokens to our message.sender, and the value is initial supply. Okay. So again, this is an event that says that there has been a transfer of this amount from this address to this address, right? Pretty simple. Okay, so we are done with our constructor. Like we initialized a couple of values like token address. We called the bank precompile via our reference, set the metadata. We even minted the tokens, and send the initial supply to the owner, which is basically the person who deploys this contract. So yeah, so that is our constructor. Now let's just go ahead and create the rest of the functions. All right. So up next, we are going to write functions that will help us get the balance and balance of addresses, and of course like total supply and all those kind of stuff. Now, as you know, like we are not storing any of those details in the contract storage. So to get those details, we need to refer to the bank precompile. So let's see how that works. So let me just create a function called balance of. Now this function is like, we are going to override this function because it is already there in the open zeppelin ERC20 contract. So address, so we are going to override it. So like account, it's public view override, and it returns a uint 256, right? And so to get that detail, we are going to have to go to bank balance off, and the token is basically the token address, and the account is basically address. So yeah, as you can see, we are getting the detail from by referring to the bank precompile. So similarly, we are going to create another function to get the total supply again. uh yeah, so we're going, again it's public view override returns uint 256, of course, given 256, and again it returns bank dot total supply, and of course it will be the token address. So yeah, there you go. We are not storing any of this in our contract storage. We are referring to the bank precompile to get these details. So the next one is essentially the transfer function. So let's just create the transfer function. Transfer. So for transfer, you know that you need a true address and you need the amount. So amount. There you go. Right. Uh, okay. And it's going to be public. It's going to be overridden, and it returns bool, which basically says whether it was successful or not. Right. Uh, okay. So first we need to do a couple of checks. The first check is we have to make sure that the address that we are sending to is not, uh, you know, zero address or a burn address. And we'll just say, see, 20, the error will be transfer to zero address. Okay, now require, we'll do another check, and the amount should be greater than zero. I mean, who sends zero? Like, who transfers zero? Transfer amount, sorry, amount must be greater than zero. Pretty you know, two basic checks. And once that is there, we're going to create a variable called owner, and the owner is going to be message.sender, and we'll just do bool success, and we'll just say bank dot transfer. So owner will be the from address, to address, and amount, right? And yeah, we'll just put another require which will say success should be true, else bank transfer failed, which is bad, which shouldn't happen, right? So yeah, and we are also going to emit the transfer event. Emit transfer. Oh wait, oh, transfer, and we're going to say owner. Again, this event is part of the ERC20. That's why we haven't declared it, because we are inheriting it, right? So yeah, and we'll just say return true. Now you can also add the operations thing, like we have the operations event also, you can add it, it's fine. Like since we are doing the transfer, I mean, yeah, I think we can just go ahead and add it. Why not? We'll just say emit, just so we know that we are using the operation. What was the name? Bank operation executed, and the operation is going to be transfer, and yeah, success, right? So yeah, we have the event also. So the next function that we are going to write is transfer from, which is like for the allowance thing. Like if you allow somebody to do the like if you have given some allowances and stuff, you use the transfer from function, right? So yeah, let's just go ahead and create the allowance again. Like the transfer from function again, all these are part of your everyday regular ERC20 token, token contracts. The only difference here is that we are just using the precompiles, right? Instead of writing all or storing all these details by ourselves, or handling all the you know uh, processes by ourselves, we are basically using the precompiles, which also returns a bool, which means if it's successful or not. Okay, so yeah, I think even for transfer from, these two require statements are basically there, right? The address shouldn't be a zero address, and yeah, the amount should always be greater than zero. So, and I guess the spender, we can say address. Oh, sorry, what happened? Okay, sorry. Address spender is going to be message.sender, and spent allowance. I think, yeah, allowance. So it basically checks and updates the allowance, right? So from spender and amount. This again, part of the ERC20, so we don't have to write all the logics here. Okay. Okay, yeah. I mean, VS Code is a bit slow when it comes to, you know, checking the errors and stuff. So you might go looking at the code because of the red squiggly line, but then it will just, you know, vanish because VS Code will finally catch up. But yeah, success equals bank. Again, here also we are using the bank transfer. I think we can just copy this. We're going to do the exact same stuff. So yeah, bank success, and the only difference is that the parameter names, like, so there is no owner here. We're going to send from, and yeah, to an amount, of course. And if it is successful, you can yeah, and we can also emit the same events. Like, it is also a transfer. We can put it as transfer. Yeah, I think we've already copied it. Transfer from, because no, I mean the operation is still transfer, so it's fine. Yeah, and we can also emit the transfer event. Transfer event, which basically says from to and of course amount. And if everything goes well, we'll just return true. Oh, true. Okay. So yeah, so there is our transfer from function. Again, you know, very basic, very standard stuff. Like, it's there in almost every other token like token contracts. Now, another thing, like, we can also add a neat little function called function support. Okay, how do I put this? Yeah, we can say function support supports bank precompiles. Okay, this is sort of like a flag. I mean, it's not a necessity. It's basically a flag. We can just put it as an external function. It is a pure function. It returns a bool, and it basically flags that this contract is supporting, you know, precompiles. So yeah, we'll just return true. There you go. So pretty standard. I mean, nothing fancy. We have a very basic ERC20 token transfer, transfer from, and we have added this neat little function that flags whether true, because our contract is using the, you know bank precompiles. So there you have it. Like, this is how we are going to create the precompile functions. And let's just go ahead and do a forge build to see if everything is okay. So forge build, it will create, like, compile it and create all the artifacts for it. So if everything is proper, you know like, if our syntax and everything is proper, we won't have any issues compiling it. So let's just go ahead and see. Okay, so yeah, I mean, everything is okay, and there are a couple of notes, meaning, like, yeah, these are not errors. Like, you can see this compilation is successful. It's just that you can try and do all these things so that your contract looks better. But yeah, I mean, it's like I said, better practice kind of a thing. But there are no errors, meaning, uh, yeah, means success, unused. Oh, wait. Oh, okay. Mint success. Oh, we have to do a require here because, okay. Mint should be successful. Else we have to put out a warning saying that mint failed, because mint shouldn't fail, right? Okay. So yeah. Now if you do the forge build again, okay, there you go. Okay, so again, you can go through all of these things, try and match the best practices so that your contract looks better. But I'm too lazy for that. So I guess, like, since we have like all the artifacts, I guess we are good to go. Now let's just go ahead and see how we can deploy this contract. Okay. All right, so we have our dev token contract set. We saw how we can use, we saw how we can basically interact with the bank precompile and handle all the data and all the processing and everything. Like, we created our own interfaces like the interface that helps us, interact with the precompile. And based on that, we have the single source of truth, or single source of data, which can be accessed both from and both from a Solidity contract as well as the Cosmos ones. And so it's much more easy, like, so for handling these tokens in both these environments, you don't need to wrap your tokens, you don't need to create bridges. You have a single instance of the token that is handled by the native bank module, and you can access it via a Solidity contract or the other one, right? So yeah, uh, so we have our contract. So the next thing that we need to do is go ahead and deploy this contract onto the test network, and maybe do a bit of testing, right? So before we get started with the test network, you have to make sure that you have uh, added the network details in your wallet, and that you have the test tokens. So yeah, like, to if you don't have the test tokens, you can always go to the faucet and get those test tokens, right? Like, I think we have already done that in our initial session sections, right? Initial part of the video, I showed you how to get the tokens. So yeah, just follow that. Now, okay, so now we can just go ahead and deploy the contract. Now we won't be writing a script, we will be actually using the cast tool that I talked about, like Foundry. When you install Foundry, it comes with this really nice terminal tool called Cast, which lets you deploy contract and interact with it and do a lot of stuff with it from terminal. So we are going to, sorry, I mean, we use Forge to actually deploy the contract and Cast to actually interact with it. Like, I'll show you how both of them work. So before that, we need to set up a couple of environment variables that we will be using in those commands. So in your folder, just go ahead and create a .env file, right? And within that env file, we need to add a couple of stuff. So the first thing is the private key of your account. Like, I'll show you how to get it, and you can just add that here. And next is the RPC URL. So the RPC URL, you can use the same RPC URL that you added in MetaMask. So we can just copy this and paste it there. Okay. So yeah, and for this one, so what you have to do is, to get the private key, go to MetaMask, click on the menu, click on account details, private key, type in your password, and just hold, and it will reveal the private key, right? Once you get the private key, you can just you know yeah, you can just copy it there. Let me just get it and copy it. 1 second. It's not that I don't trust you guys, but if somebody like Patrick Collins see me actually revealing the private key, he might just come after me on Twitter. So yeah, let's not do that. So let me just quickly paste the private key. Okay. All right. All done. Okay. So yeah, I've added the private key, and you know how to retrieve it. So add your own private key to the .env. So once you have that, what you need to do is, let me just clear the terminal. First, just source the .env so that your terminal can access all those variables. So I'll just say source.env, and now we can access all those values, right? So the first command that we are going to use is forge create. Now, forge create, this command, what it does is it helps you basically deploy your contract. So forge create, then we have to give the contract address, like location, dev token dot sol, like source dot dev token, and within that we are trying to deploy the dev token contract. Now we can provide the RPC URL, and since we have sourced it, we can just put it like this, and it will fetch the value from the environment variable, like RPC URL, and of course the private key, right? And again, you can give private key, right? and you can provide the value. Now this is what I said, like we need to provide a token value, so that it gets passed to our constructor and it can use it to actually interact with the uh, you know precompile, like the bank precompile. So the value is 1 followed by, I believe, 3, 6, 9, 12, 15, yeah, 18 zeros. So yeah, which is basically one injective token. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. Yeah. And you can just put a couple of flags. We can just handle it the legacy way. And to broadcast to an actual network, we'll just put the broadcast file. Cast. Okay. So this will basically put your contract onto the test network. Let's see if it works or not. Let's go. So you can see that the compilation already happened, so it won't. Yes, we have our contract deployed to the testnet, right? Like it uses the RPC URL, it uses the private key and everything. And if you look at your account right now, if you look at the account right now, you can see the token. Yeah, there you go. Like there is a change in the token amount because we have used it to create the or deploy the contract. Now you can go ahead and actually see the explorer. Like you can just, 1 second, wait, where is the, yeah, okay, let me just get the token explorer. Okay, 1 second. Okay, so yeah, you have the injective testnet explorer. You can paste your address there and you can see it, right? Like the address is created, like the token address is created. There you go. So that means our contract has been deployed onto the test network, and now we can interact with it. Like I told you that we can use the cast tool to actually interact with the contract. So you have the token address here. So what we are going to do is we are going to call a function. So cast call, we're going to do copy this, paste the contract address there, and we are going to say we need to get, let's say, the total supply. So we have the function here, right? Like the total supply function here. So we are going to say supply, and I don't think it takes any parameters, but it does return a uwin 256, right? So close the whole thing, and we just have to provide the RPC URL. Okay, and of course PC URL. Okay, and you can see, right? You can see what happened. You can even try and call our function, like our custom function, which is like, yeah, support precompile. Let's just see, and let's just see what this returns. So it doesn't take any parameters, but it does return a bool, right? So if we call that, it will return true because it is true in our contract. You can even get the address, right? So I'll just do this cast call, RPC, and everything remains the same. So here I'll just give balance of, and so this takes in an address and it returns a uint 256, right? And after that, I think I should give my address. Like you can just copy your MetaMask wallet address because that is the address. So you'll just copy it, and yeah, and let's just try this. Yes, and we have the balance. Like we basically have the total supply as our balance because in the constructor we did the same thing, right? So there you go. Like we have successfully created a contract that interacts with the bank precompile, and we have created a token and we have put it in testnet, and apparently everything is working fine. So yeah, there you go. I mean, like we've discussed a lot of stuff in the video, and I hope a lot of these things are clear. Like you can always reach out to the Web3 Compass community if you have any questions or doubts. And from here, I think the next logical step is to build something cool. Like we already saw how to use the bank precompile, so you can build cool stuff with it. You can even try out other precompiles, like there are a lot of them. Like if you go to the oh wait yeah oh sorry about this. If you go to the docs, you can see that there are lots of other precompiles like bank, exchange, all those things. Staking, exchange, all those precompiles. So you can try and use that and create some cool stuff with it. But yeah, I guess that's it. Like we have our dev token contract that uses precompiles, and basically we have created one instance of a token that can be uh, accessed via Solidity as well as whatever we write in Cosmos. So, yeah, that's it. So, see you around and happy building.